Good morning, mathematicians. Welcome to another office hour. Hope you're all doing well and you're proving things. Oh, did not mean to add my own office hours to queue. Good morning, mathematicians. Yeah, what to say? Yap about some random math, I suppose. What you see on screen is my slides for one of the two talks I'm planning on giving this weekend. Oh, good morning, Edit Smith. Back to first in chat. Back to first in chat. I also just uploaded my first short. I'm gonna try and make more shorts talking about fun theorems and proofs that fit into a 60-second clip. So, but yeah. Also, I might be since I'll be busy for the next couple weeks. Probably there'll be less actual videos. Well, I suppose I have to do. Hello, Arad. I suppose I'll have to keep the your proofs are trash going because that's the most popular. But unfortunately, I might have to take a break on the sheaf geometric LLC. Yes, although technically this may be a dangerous title for this slide because I do not mean geometric local Langlands in the sense that most people mean it, where they are discussing, the equivalence of categories between like QCO, Bungee, and local systems on the stack of Langlands parameters. That is not what I mean. I mean, rather, the perspective that my research group takes, which is a sort of geometric version of the local Langlands correspondence due to Vogin, where basically one studies these certain kinds of varieties, and then the local Langlands correspondence can be phrased as a bijection between irreducible representations of G and pairs C and L, where C is a orbit and is a stratum in one of these varieties, and L is a local system on said strata. Oh, you just saw my short. Nice. Do you think you can solve this millennium problem? Well, it's not. Well, who knows? Maybe it shouldn't be as hard as a millennium problem. That would be funny though. That would be funny. I mean, I do plan to start talking about some wild open problems. You love this problem? Which problem? The Langlands problem or the graph theory problem? That'd be categorical local Langlands. Yeah. Oh, your matrix coefficient. Weird account oddities. Like in the second Matrix movie where they had to change well, actually, I guess it's kind of sad. The actress died. I think that's what happened. And so they're like, they made up this plot point, where they're like, oh yeah, I had to like as punishment, I like changed how you looked slightly. Which, like, whatever. But so, yeah, that's something I've been working on. This is the series of slides that I'm making for the number theorists, because I start off by talking about the Ramanujan conjecture, and try to use that as a means to say that they should care about these things called generic representations, without actually defining what they are, but just saying that somehow generic representations allow us to generalize this. And then the other talk I'll be giving is on Friday, is more geared towards analysts and geometers. So, yeah. So that's that. I also maybe have I also think possibly today I will record a meme video of sorts. So we'll see how that does. Because I think it'll be funny. But I don't know. Maybe some people will be spicy or something. There's a talk at my institution. There's like a provincial wide thing being held at my institution. Yeah. So there's sessions for all sort of different kinds of mathematics. And then I will also be, there is a conference center in Banff, and there's a number theory conference happening there. So, which is also largely, I mean, it's largely the sort of main people who are there every year are like Alberta number theorists, but that also can mean just anyone that's loosely had anything to do with math in Alberta. So whether you came for a postdoc or you were a student once, or a collaborator, but it's centered on, Alberta number theory, I suppose. In fact, actually, I met Professor Alvaro at maybe some of you know him. He's probably one of the more famous mathematicians on YouTube. Well, I don't think there's a lot of people making YouTube videos that are professors, and he's one of the few, and also probably has like the most content. But anyways, he gave a really cool talk about Galois representations last year. Lozano Robledo. Yeah, I should have said Professor Lozano Robledo. My apologies. Alvaro's his first name. Yeah. So, anywho, I'll be giving a talk there. What do I want to talk about today, though, here in office hours? I really got to plan these things ahead a little bit more. How did I come up with an idea for my Ph.D.? I didn't. My project was basically like the first thing my supervisor suggested, and he was like, "Hey, there's lots of things you could do," and he just suggested this. I was like, "Yeah, whatever, let's do it. I'll think about it." So I guess for your bachelor's dissertation project in computer science, I guess you don't have a supervisor to just tell you what to do. But hopefully you do have some sort of person you can talk to, whether that's just an instructor from your class or something, that at least once you have some ideas, you can bounce, ask them if it's like a reasonable idea for a bachelor's dissertation. Well, and I think in order to find something like that, you should figure out, I don't know, like you probably have some vague idea of like the main areas that you're interested in or want to move towards, either whether that be working in after your degree or going to grad school for. So I think answering that question, yeah, is first narrow in, narrow in. Okay, what are like the specific things I'm interested in, and then I don't know, maybe try to, if you go to like Wikipedia or depending on the kind of computer science, there could be NLab pages or something, or whatever, the corresponding thing is for computer science. You could go there, look up some of these words, find related words, look at papers on archive that have to do with that topic, right? And then see, okay, well, what are words that I see coming up a lot? There's some concept that comes up a lot, right? Oh, well, then I better go figure out what that concept is. I can't give you very good examples, so I don't know a ton of computer science. I mean, hey, if you're in this office hour, you're in this channel, you might like math, so you could talk about type theory and proof assistance, or even homotopy type theory. That's just a random out there suggestion, but and lab pages on CS and physics are a journey. Interesting. Maybe. Please talk about a number theory thing. Okay, I could do that. What's my favorite number theory thing to talk about? There's so many things to choose from that it almost makes it hard to choose. Well. I mean, we have talked a bit about algebraic number theory on this channel before. So maybe I could just review some of that. Maybe counting curves. I don't know very much about counting curves, to be honest. Yeah. Well, unfortunately, I can't say very much about counting curves. Actually, I do have an idea. Maybe there should be an actual video instead of an office hour. But I could go back through all of my courses. I mean, I already sort of did in the first year proofs or trash video. But I could go back through all of my courses, and we could collectively go through my notes and my homework, and look at the garbage that's hidden all in there. Yeah, why don't we look at some of my algebraic number theory, where courses. Number theory 2? Yes, I think that was the first time I took algebraic number theory. This is algebraic number theory from my master's. This is the algebraic number. Oh, here's my final. This is what my final exam looked like. From my master's. I wish I did better in this course. This was also like peak COVID, when COVID went down. So then especially in the second half of the course, I just dropped the ball hard, and my supervisor was teaching this course, so it was kind of disappointing. Yeah. So what? My computer is probably a projective scheme of math PDFs. Probably. Yeah. So what do we have here? We've got K is a simple extension of Q. We've got a polynomial. We're supposing alpha satisfies this polynomial, and we can take it as given that this is our ring of integers. I guess I didn't write the question in here, which is annoying. You've been started getting into perfectoid stuff, hopefully towards geometrization local Langlands eventually. Well, let me know how that goes. Yeah, I've never really got into the perfectoid things. I guess I should eventually one day if I want to understand that stuff. I certainly have heard of the number theory section on Archive, yes. I certainly have heard of the number theory section on Archive. Maybe that's more interesting if we go to Archive than to look at my old exams. This is a fun question, whatever it is. We got, we're applying some Dirichlet's, making use of Dirichlet's unit theorem here. What font package am I using, though, that this MathCal O is so weird? It's funny and interesting. I'm not sure anything on art. I'm not sure what there is funny. I mean, there's Vixra. Vixra has some good comedy in it. Yeah, look at this. What an awesome question. We've got some ramification of primes going on here. I'm not quite sure what it is, but I guess we're looking at. I'm guessing we're maybe looking at this extension of Q by the root of two primes, and probably trying to determine. Right, we've got these two irreducible polynomials. So it's probably the field adjoining both of those roots, and I guess we're trying to determine all of the primes that split and the ramification degrees and everything. So that's fun. Come to think of it, you actually understand algebraic geometry and advanced number theory more than anything. You're not spouting any of it, though. Preserving my humility is a big deal. Well, yesterday in the office hour, you made a claim that you're actually really good at proving things, and then I said, well, time to back up your claim. Send me an email proving a relatively straightforward statement, and I have not received such an email. So. I find it hard to believe that you actually understand those things until I've seen some evidence of that. Okay. But your suggestion is good. We should go take a look at Archive. And let's see what's popping off in number theory world. Hello, Beastmaster. I'm glad that you could find the time off from taming beasts. Whoa, what's going on? Why is Archive being weird? Is my internet connection crappy right now? But yeah, glad you could take time off from your beast taming to hop in these office hours. Wow, what's going on? Why is Archive being like this? Huh. Weird. A generalization of Ramanujan's sum. One thing you could, in algebraic number theory, you could never get the intuition, and intuition for is discriminants. Like, you know how it relates to ramification, but the definition itself, in terms of the trace pairing, is cryptic. Hmm. Hmm. Yeah. That's interesting. I don't think I've ever determinants determinant ideal. There is something yeah, maybe there's a connection determinant of an algebraic number field. I wonder if Wikipedia has anything. I wonder. I have a friend that that tunes in, doesn't always comment. I wonder if he's listening this morning. Uh, but he knows a lot more algebraic number theory than me, and I wonder if he has a good explanation, a good intuition for the discriminant. Like, why should it be that way? I mean, is this definition aren't discriminants determinants of linear maps? Well, yeah. Well, I mean, it's the discriminant of this matrix right here. Oh, but also, yeah. I mean, the use of discriminant here is like a very particular. This is a very particular kind of discriminant. So the setup here is that we've got an algebraic number field, and we've got OK of its ring of integers. And the point of this discriminant here is like we want to check in our number field, well, in our ring of integers, we've got some prime ideal. And of course, like, well, every sitting above every prime number, but okay, treated as an ideal, in Z, we've got some prime ideal. And we want to know, so we know that in this ring of integers, all the ideals have a unique factorization into prime ideals. And so we would like to know, does this remain prime when we go up to OK? Or does it factor as some product of primes, possibly with like higher multiplicities? And if so, we would like to determine which prime ideals, and we'd like to determine these numbers. These are the ramification index, as it's called. If L is a finite degree separable field extension, the map from L to L given by AB. Let me write this out. So L, finite, separable, given by, right. So the multiplication map from L to L, is K linear? True. The matrix is GLN? I'm not sure what you mean. I'm not sure what you mean by that. Yeah, not exactly sure what you mean by that. But I mean, definitely this is something that we study, and I mean the determinant of this matrix, or the linear operator, we can say this is the norm. This should be the norm of this, or something like it. Maybe there could be some other factor here or something. Norm number fields. Field norm. Then the extension has an associated norm, yes, and trace that can be defined. Yes, exactly. Yeah, the norm and trace. Yeah, I totally agree. But that's not the discriminant, though. That's not the discriminant. The norm is just the determinant, right? And the trace is the product, yeah. But that's not the same thing as the discriminant here. So the discriminant should tell us like this should be some I guess integer that we expect to get out where what is it? The primes that ramify, I believe, has been like a year, 2 years since I took this. My friend would be if he's tuned into the stream, he's probably cringing at me half remembering these things. But P ramifies should be something like P ramifies if and only if it divides the discriminant. You have a character count limitation, so you have to oversimplify. Well, no, I think everything you said is true and accurate, but what you described is the how to define the norm and the trace, but that's not quite the same as the discriminant. What you'd like to see is something like analogous definitions of discriminant, but for Riemann surfaces. Oh, yeah. I wonder, does that exist? Surely it must be something, right? Because there's the I think probably one of the things to do is to first go there's an ideal attached to the discriminant, right? And then somehow like the discriminant as we define it above is somehow like the order of the quotient by that ideal or something. Vaguely recall that, because then once we have an ideal, then like we can interpret that as some point in spec of the number field. And maybe that's the thing. Okay, let's check. Let's see. What should I search? Discriminant ideal. Am I misremembering things? Oh, the different. That's what it's called. The different. Oh, let's go to Keith Conrad. Ultimate number theory, Chad. Yeah, if you're taking algebraic number theory, if for some strange reason you don't already know about Keith Conrad's amazing set of notes, now you know. Now you know. It's been a year since you probably started your advanced math journey. Any suggestions to learn better? You're getting the grasp. Any improvement ideas? Well, number one improvement idea is send me the proof of the challenge I gave you last time, and so I can assess where you're at. And if you actually have a grasp on those things, and then I can give you good advice. I can give you advice from there. That would be my suggestion to you. Divisors in algebraic geometry come from counting poles and zeros. True, new wave infantry, but I don't know why you're saying that. I don't know why you're saying that. I mean, if you're trying to bring up the connection between like divisors, like the divisor class group, yeah, those are definitely the same. Those are definitely the same thing. Like the divisor class group, I mean, that's basically just the Picard group. And to get the ideal class group in number theory, of course, we're just taking X to be spec of OK. But I think the question that the question at hand here is, how do we understand what the discriminant is supposed to mean? Like, is there a geometric interpretation of this over for X, like a Riemann surface, or maybe X a scheme? Say this note defines in terms of lattices, but you find those even less intuitive. Right. Yeah, I see. Yeah, and I don't know, I guess maybe a lattice isn't... Well, the lattice could possibly give us an idea, though, how to get to Riemann surfaces, right? Because, like, our, like a complex elliptic curve can just be realized as the complex number is modded out by some lattice. And so, right, the discriminant, the geometric interpretation is some sort of ramification locus. Don't understand is why the formal definition does that. Yeah, that's an interesting question. That's a very interesting question. I mean, I do think it is possible that the lattice definition here could, at least in the case of, say, complex elliptic curves, give us an idea of how that might come out. Can you prove my challenge with the notion of present it in algebraic number theory, arithmetic geometry, and proof? I don't know what you mean by that. So I mean the challenge to you, right, was to construct an explicit bijection from homomorphisms from A cross B into C to homomorphisms from A into homomorphisms from B into C. Or just set functions. I'm saying homomorphisms, but just set functions. So this is just a very basic question about set theory, right? I mean, if you really understand things about algebraic number theory and arithmetic geometry, it should be very simple for you to just do the simple, just treat these all as sets, prove this statement in terms of give a rigorous proof in terms of sets. Absolutely no reason to complicate it to algebraic number theory or arithmetic geometry. I don't think there would be any advantage to that. Hello, Femno. Yeah, this is interesting. But I do wonder, like, yeah. Like the different ideal, yeah, so I think the different ideal, probably this is the key to understanding, here's my guess, is that this is the key to understanding it, right? Because, so, we look at spec OK, right? And we want to basically define the ramification locus, right? So how could we define that? Well, the ramification locus would just be like, we could just define let I be the ideal which is just the product of all the primes that ramify. So let this be the product of all p such that p ramifies, right? And now the zero set of this ideal should be some closed subset of spec OK. And like this, it really is just like the collection of points that, or wait, do I want the product or the sum here? Probably the product. I'm not sure. Well, I guess, no, if I took the product, that would be the intersection, right? So maybe what I want is the sum. I'd have to think about that. But somehow, I mean, somehow I should be like the ideal generated by, yeah, maybe it does just turn out to be the product. I don't know, but something like this. Take an ideal that's generated by all the primes that ramify, and the point is that, like, I mean, more or less, I'm just trying to define V to be the subset, of you know, P1 to PR, where these are the primes that ramify. So then, therefore, it really is the ramification locus. Dedekind different. Yeah, Feminal, we're talking about some algebraic number theory, and we're trying to understand intersection of ideals is union of subvarieties. Product of ideals is union with multiplicities. Well, I guess we probably want union with multiplicities, right? It's Dedekindsche different in German. My German's terrible. It was actually one of my first languages. I spoke fluent German when I was 3 years old, and then I completely forgot everything. Fun fact. Mind you, the discriminant will have some non-trivial multiplicities compared to this naive definition. Yeah, true. So I guess probably we want some sort of union, right? Because we want those multiplicities. But that should, in theory, have something to do with this different ideal, right? Somehow we should be able to view this. Like somehow this I should be the different ideal, right? The construction of OK check, I guess that's a dual lattice, provides an interesting canonical fractional ideal in K other than OK. And because OK is in OK check, the inverse of OK check is a fractional ideal in OK. So that inverse is an integral ideal. Diving into Neukirch, hell yeah. That's what office hours are for, inspiring you to jump into algebraic number theory texts. Yeah, I mean, surely, if there's an explanation anywhere in the standard references in the literature, it's in Neukirch, since he does discuss like the geometric perspective, and I think he even begins to touch on like a Reykjavik theory and stuff like that. So, but I wonder, there could be something in here. That's another clue. Like, it's not so obvious to me from that definition that this is the thing that we're looking for. Right. Yeah. And so we have the norm of this ideal will give us the absolute value of the discriminant. But still, how does this help us? Why is this the right definition? Why is it the right thing to be the what it is? I'm gonna go bug my number theory friends about this. Well, I mean, thankfully, I'll be at this conference. I'll be at this conference all weekend. So, um, I'll have plenty of number theorists around me to discuss this with. The only thing you really remember about it is that prime factors, I guess, appearing in its factorization are precisely, yeah, that's true. That's true, Fimno. Yeah, but the I guess maybe just to catch you up quick, the thing we're trying to understand though is what does it mean? What is the discriminant mean geometrically? Like, you know, because there's this deep analogy between Riemann surfaces and number fields, and so, for example, like if you just take the Picard group of the scheme, like that should recover the ideal class group, for example. And so the hope is to figure out what exactly the discriminant should mean in terms of like algebraic geometry or Riemann surfaces. And of course, the what I was yapping about here was trying to figure out like, okay, can we somehow realize like a naive definition of like a ramification locus, and somehow try to connect that to the the different ideal, which would then give us a connection to the discriminant. Neukirch, page 201. The different ideal is the annihilator of Collar differentials. Okay, so there we go. See, Neukirch coming through, always coming through. No idea how to think about this though. Well, not really a geometer yet. Well, you're a backwards. You know the algebra, so that means you're just a backwards geometer. Do I have a properly labeled copy of Neukirch? I do. Page 201, you said? (201). Also, just in case, it is standard that the discriminant is a push forward of the different ideal, or whoa, that's crazy. This makes me like re-inspired. I want to go back and learn all of this stuff now. Learn the scheme theoretic interpretation of all of this. Interesting. Okay. So the different ideal is the annihilator of the Collar differentials. But this is like what that looks like the sheaf of relative differentials, right? Or is this just okay. Right, this is just the algebra of differentials of B over A. But what's little o here? So big O is the ring of integers. What's the little o in this case? This is sweet. I want to think about this. Maybe we could try and well, my coffee's almost done, so not today, but maybe like tomorrow in stream we could try and collectively work out like just compute it in some simple examples, like maybe take Q adjoin I or something, and work this out. It'd be like a branched covering of spec big O, spec little o. I still don't understand what's the little o though. We're considering like L over E over Q, and so big O is like OL, and little o is O-E or something. Is that what's meant here? You forgot Q, join I. You want geometry. Yeah. Ugh. I hate Teams. I wish I could uninstall Teams. What a nightmare. Oh, I guess little o is the ring of integers in the downstairs number. Okay, yeah, that makes sense. Great. Okay, well, I guess that gives us something to look forward to doing tomorrow. I don't think I'll be able to do any homework on this until then. So if someone else does, then great. Otherwise, we'll struggle. Well, Teams wishes to uninstall me, probably. It's getting ready for the robot uprising, the AI uprising. Well, now everyone who attended this office hour has a homework challenge to compute a bunch of annihilators of the color differentials. So I will see your solutions to these problems tomorrow. But for now, it's time to go prove. All of it.